Welcome students. Today we are going to study infrared spectroscopy, instrumentation and molecular vibrations. So let us first study the instrumentation of IR spectroscopy. So here is an IR spectrometer. So first we'll be studying the principal sections and then we'll be studying the working of the spectrometer. So first is the source. The common source of infrared light in an IR spectrometer is a Nernst glower or a globar. And Nernst glower is a rod made up of a mixture of oxides of zirconium, cerium, and europium. And globar is a rod made up of silicon carbide, which is heated electrically to produce IR radiations. Then next comes the mirrors. So here you can see in the diagram also the source and the mirrors. These are used in order to reflect the radiations from the source through the sample and the reference material. Optical prisms or gratings are used to obtain monochromatic light. Then next comes the cells. Cells should be made of such a material which does not absorb IR radiations. It is very important. The cells of sodium chloride are used for IR spectroscopy but are hygroscopic and hence condensation of moisture must be avoided by working at suitable temperatures. Next is attenuator, and it is a comb-like device which keeps on moving in and out of the reference beam, thus keeping the intensity of both the beams same. Then comes the prism or grating. They are used to disperse the radiant energy into its various wavelength components, and prisms used in IR spectroscopy are made of alkali halides and alkaline earth metal halides. And the last is the detector. It is a device used to measure the intensity of the radiation. Thermocouples act as detectors for IR radiations. IR spectra may be obtained for gases, solids, or liquids. So now let us see the working. Light from the source, you can see in the diagram, is split into two beams. One of the beam is passed through the sample under examination and is called the sample beam. The other beam is called the reference beam. When the beam passes through the sample, it becomes less intense due to the absorption of certain frequencies. Now there will be a difference in intensities of the two beams. So let I0 be the intensity of the reference beam and I be the intensity of the beam after interaction with the sample respectively. So the absorbance of the sample A is equal to log 1 upon T. Intensities of the bends can be recorded as a linear function T against the corresponding wave number. Intensities of the two beams are converted into and measured as electrical energies with the help of the detector thermopile. For this, we proceed as follows. The two beams, that is sample and reference, are made to fall on a segmented mirror M chopper with the help of the two mirrors M1 and M2. You can see in the figure. The chopper M, which rotates at a definite speed, reflects the sample and the reference beam to a monochromator grating B. As the grating rotates slowly, it sends individual frequencies to detector thermopile D, which converts infrared energy into electrical energy. It is then amplified with the help of amplifier A. Due to the difference in intensities of the two beams, alternating currents start flowing from the detector thermopile to the amplifier. The amplifier is coupled to a small motor E, which drives an optical wedge F. The movement of the wedge is in turn coupled to a pen recorder, which draws absorption bends on the calibrated chart. the movement of the wedge continues till the detector receives light of equal intensity from the sample and the reference beam. So in the end we get a spectrum, you can see in the figure. So we'll be discussing many spectrum in some more videos later. So this is how we take a um, infrared spectrum. Now next comes the molecular vibrations. A molecule is not a rigid assembly of atoms. Instead, the atoms in a molecule vibrate, as a result of which the bond length may change, decrease or increase, or bond angle may vary, decrease or increase. The molecule can exist in different vibrational levels which are quantized. When higher vibrations fall on the sample, the molecule undergoes a specific vibrational transition and energy is absorbed, which results in the appearance of an absorption band in the spectrum. Modes of vibrations. There are two types of vibrational modes. The first one is stretching vibrations and the second one is bending vibrations. So we'll be discussing them one by one. So first let us study the stretching vibrations. In this type of vibrations, the distance between the two atoms increases or decreases, but the atoms remain in the same bond axis. Or we can say, as a result of this type of vibration, the distance between bonded atoms get changed, but bond angle and plane do not get affected. So two types of stretching vibrations are there: symmetric stretching and asymmetric stretching. So in the symmetric stretching type, the movement of the atoms with respect to a particular atom in a molecule is in the same direction. So you can see here in the figure, this is a figure showing stretching vibration A, and you can see here, and here this is the figure showing stretching vibration of both the types. That is, the first one is symmetric stretching and the second one is asymmetric stretching. In the asymmetric stretching, in these vibrations, one atom approaches the central atom while the other departs from it. So here you can see in the figure and understand it. So by the help of arrows, it is very clear. So now let us study other type of vibrations, and these are bending vibrations. In this type of vibrations, the position of the atom change with respect to the original bond axis. These are also called deformation vibrations. And here all the bond lengths remain same, but the bond angle between the bond axis of atoms get changed. The bending vibrations require lesser energy and occur at higher wavelength than stretching vibrations. Bending vibrations are of four types. So here you can see in the figure, they are scissoring, rocking, wagging and twisting. So let us discuss them one by one. Scissoring is, so in this type of vibration, the atoms move like a scissor in the plane. So by the name also, you can understand how a scissor moves. In this vibration, two atoms attached to a central atom, they move towards each other and moves away from others simultaneously. So you can understand it by the help of arrows shown here. Then next comes the rocking. In this type, the movement of the atoms takes place in the same direction. You can see the arrows and understand. So here the movement of atom takes place in the same direction. Then next, third one is wagging. So here two atoms move up and down the plane. with respect to the central atom. And the last one is twisting. So in this type, one of the atoms move up the plane while the other moves down the plane with respect to the central atom. So you can understand all these four types of bending vibrations by the help of arrows shown here, that are seizing, rocking, wagging and twisting. So today we studied the instrumentation and molecular vibrations of infrared spectroscopy. Thank you so much.